All right, let's dive into something that could completely change the way you see machine learning. Imagine you're a detective, solving cases, separating truth from lies, and finding the one crucial piece of evidence that changes everything. Now, what if I told you that a machine learning algorithm does exactly that? It picks out the most important pieces of data, draws a clear decision line between different cases, and works tirelessly without a single break. Enter support vector machines, one of the most powerful tools in the world of machine learning. We're about to embark on a journey that will uncover how SVMs work, how they create decision boundaries, and why they're so effective in high-dimensional spaces. Think of it like playing chess, but instead of just looking at the pieces, you're playing on a board with 100 dimensions, and SVMs still manage to find the best move. We'll break it down step by step, moving from the basics of hyperplanes and margins to advanced concepts like kernel tricks and real-world applications. But before we get there, let's set the stage. Picture this: you're building a model to recognize handwritten digits. Your dataset is massive, thousands of images, each with hundreds of pixels. How do you separate a 3 from an 8 in a way that's both efficient and accurate? A simple line won't do, and the data is too complex for basic methods. This is where SVMs shine. They not only find the best dividing line, but can also transform data into higher dimensions where separation becomes easier. By the end of this session, you'll understand not just how SVMs work, but why they are so powerful. And trust me, some of what we'll discuss might just surprise you. Ready to get started? Let's jump into slide 1 and unravel the mystery of support vector machines. For the start, let's set the stage for something big. Have you ever watched a tightrope walker balance effortlessly on a thin wire, defying gravity with every step? Now, imagine if I told you that this delicate act of finding balance isn't just reserved for acrobats, it's at the very heart of one of the most powerful machine learning algorithms we have: support vector machines. This algorithm isn't just another way to separate data points, it's a masterclass in precision. While other models might just draw a dividing line and hope for the best, an SVM works differently. It meticulously finds the best possible boundary, ensuring the largest possible gap between different groups. Why does this matter? Because a model that creates a wide margin between categories is a model that can make better predictions, even on brand new, unseen data. It's like being able to ace an exam by studying only the 5 most important pages instead of the entire textbook. Picture this: you're in a crowded train station. There are 2 groups of people, one on the left, one on the right. Your task: put down a rope that keeps them apart. You could place it randomly and hope nobody crosses over, or you could carefully measure the closest people in each group and find the absolute best position for the rope so that both sides have the maximum space possible. That's exactly what an SVM does. It doesn't just find a way to separate data, it finds the optimal way. And here's where it gets even more fascinating. Not all data is neatly separated. What if the categories twist around each other like a spiral? What if no simple line can split them apart? That's where SVMs bring out their secret weapon: kernel tricks. This is where an SVM takes a problem that looks impossible and transforms it into something that's suddenly solvable, without you even realizing what happened. This is why SVMs are used everywhere, from facial recognition to spam filters to medical diagnosis. They don't just classify data, they analyze, optimize, and adapt, finding the perfect balance just like that tightrope walker. And just when you think you've got it all figured out, there's something even more surprising waiting around the corner. Because an SVM isn't just about lines and margins, it's about something deeper, something that happens behind the scenes. Let's take a closer look at what really makes it tick. Imagine you're standing in the middle of a vast open field. Your job? To draw an invisible wall that perfectly separates 2 groups, one on your left, one on your right. Simple enough, right? Now, what if I told you that this isn't just a thought experiment, but the very foundation of how support vector machines make decisions? This invisible wall is called a hyperplane, and it's the key to everything. At its core, a hyperplane is just a boundary, a mathematical wall that divides space into two distinct halves. In 2 dimensions, it's simply a straight line. In 3 dimensions, it becomes a flat plane. But here's where things get mind-blowing. In higher dimensions, 4, 5, 100, it's something you can't even visualize. Yet it works just the same. An SVM doesn't care about how many dimensions you throw at it. It will always search for that perfect hyperplane, but not just any hyperplane will do. The magic of an SVM lies in finding the optimal one. That means maximizing the distance between the boundary and the closest data points on either side. These critical points are called support vectors. Why does this matter? Because the farther apart the margin, the better the model can generalize to new unseen data. A hyperplane with a large margin is like a well-maintained highway, clear, efficient, and safe. A poorly placed hyperplane, that's like a narrow, winding alley, prone to mistakes and accidents. Now here's where things get interesting. What if you have data that's not perfectly separable? What if there's no straight line that can divide the groups cleanly? Do we just give up? Not a chance. This is where the SVM brings in some of its most powerful tricks. Adjusting for complexity, softening the boundaries, and, when necessary, transforming the entire space itself to make separation possible. Because, after all, the real world isn't neat and tidy. Data is messy, tangled, and full of surprises, and yet SVMs somehow manage to cut through the chaos with a level of precision that feels almost unnatural. But here's the real question. What happens when even the best hyperplane isn't enough? When our invisible wall fails, how does an SVM bend reality itself to find a solution? That's when things really start to get exciting. All right, now here's where things start to get tricky. Up until now, we've been assuming that our data plays nice, that there's a clear straight line that can separate everything perfectly. But let's be real. The world isn't always that simple. Data can be messy, unpredictable, and more often than not linearly separable. So what does that mean? Imagine you're trying to divide two groups of points on a piece of paper. If they're neatly arranged on opposite sides, a straight line does the job perfectly. But what if the points are scattered all over, tangled together like a bowl of spaghetti? No single straight line can separate them. This is the problem of linear separability, or more accurately, the lack of it. And here's where a lot of algorithms throw in the towel. Traditional linear classifiers like logistic regression struggle when there's no clear boundary. But an SVM, it sees a challenge and adapts. It has two incredibly powerful tools at its disposal. First, it softens the rules a little. Instead of demanding a perfect split, it allows a few misclassified points in exchange for a better overall separation. This is called a soft margin, and it helps SVMs deal with real-world data that isn't always neatly separable. But sometimes even that's not enough. Sometimes the data is so tangled that a straight line is a lost cause. That's when an SVM does something that feels almost like science fiction. It changes the way it sees reality. It stops trying to separate the data in the space it was given and instead lifts it into a higher dimension where a clean separation suddenly becomes possible. Imagine trying to separate two groups of dots arranged in a circular pattern on a flat surface. No straight line can do the job. But what if you lift the entire thing into a third dimension? Suddenly, a simple flat plane can slice through the data effortlessly. That's exactly what SVMs do with something called the kernel trick, a technique that lets them project data into higher dimensions without actually computing all the complex math that would normally be required. But wait, what exactly is this kernel trick? And how does it transform seemingly impossible problems into solvable ones? That's where things go from fascinating to downright mind-blowing. All right, now we're stepping into the wild side of machine learning, where simple lines just don't cut it anymore. Up until now, we've been working with the idea that a clean, straight hyperplane can separate our data. But what happens when the data refuses to play by those rules? What if it twists, bends, or overlaps in ways that make a simple split impossible? Welcome to the world of nonlinear data, the kind that breaks traditional classifiers. And let me tell you, it's everywhere. Imagine a dataset where two classes are wrapped around each other in a perfect spiral. Or picture the classic XOR problem where two groups are mixed in a checkerboard pattern, one in the top left and bottom right, the other in the top right and bottom left. No single straight line can separate them. If you tried, you'd end up frustrated, stuck in an endless loop of bad predictions. This is exactly the kind of problem that breaks traditional linear classifiers. They simply weren't built for it. A logistic regression model, for example, would stare at this mess and shrug. But an SVM, it doesn't just find a way, it creates one. So how does it do it? 2 words, kernel trick. Instead of trying to separate the data in its original form, an SVM takes a completely different approach. It projects the data into a higher dimension where separation becomes possible. Imagine trying to divide a set of concentric circles with a straight line. Impossible, right? But if you lift those circles into a 3-dimensional space, suddenly a simple flat plane can slice between them perfectly. That's exactly what the kernel trick does. It allows an SVM to reimagine the problem, transforming an unsolvable mess into something clean and structured. But not all kernels are created equal. Depending on the problem, different kernel functions like polynomial, radial basis function, RBF, or sigmoid can completely change how an SVM sees the world. And choosing the right one, that's where things get really interesting. Because while the right kernel can unlock hidden patterns, the wrong one can lead your model straight into failure. So how does an SVM decide which kernel to use? And what happens when we push this concept to the extreme into complex real-world applications like facial recognition or medical diagnosis? That's where we're headed next. All right, now we're stepping into the real power of support vector machines, the kernel trick. If SVMs were superheroes, the kernel trick would be their secret weapon, their ability to bend reality and solve problems that seem impossible at first glance. We already know that a straight line isn't always enough. Some datasets are just too complex, too twisted, too tangled. If we stick to linear thinking, we're doomed. But what if we could reshape the problem itself? What if we could lift the data into a new space where separation suddenly becomes obvious? That's exactly what kernel functions do. Instead of struggling to separate data in 2 dimensions, an SVM applies a transformation, a mathematical magic trick, that projects the data into a higher dimensional space where it can be separated. And the best part, the SVM never actually has to compute this transformation directly. Thanks to the kernel trick, it gets all the benefits without the massive computational cost. Let's break it down with an example. Imagine you have 2 classes of data arranged in concentric circles, like a bullseye on a target. No straight line will ever separate them. But what if, instead of trying to divide them in 2D, we lift the entire thing into 3D? Suddenly, one group forms a lower ring, and the other group rises to form a dome above it. And now, a simple flat plane can slice right between them. This is what kernel functions do. They map data into higher dimensions where linear separation becomes possible. But not all kernels are the same. Choosing the right one is like choosing the right tool for the job. Here are some of the most powerful ones. Linear kernel works well for data that is already linearly separable. Simple, fast, and effective in text classification. Polynomial kernel captures more complex relationships by considering combinations of features useful for image recognition. Radial basis function, RBF. Kernel, the the most popular choice, ideal for datasets with intricate nonlinear patterns, think facial recognition, medical imaging, and bioinformatics. Sigmoid kernel, inspired by neural networks, though not as widely used in practice. Each of these kernels changes the way an SVM perceives reality, making it capable of handling data that would otherwise be impossible to separate. But there's a catch. The choice of kernel isn't always obvious, and picking the wrong one can lead to overfitting, underfitting, or just plain bad performance. So how do we choose wisely? And how does an SVM balance complexity with generalization? That's where the next challenge begins. Now that we know how SVMs use kernels to reshape reality, let's talk about what truly makes them so powerful: the margin and the support vectors. These two elements are the reason SVMs can generalize so well and make accurate predictions, even on unseen data. Imagine you're building a fence between two groups of people. Your goal isn't just to separate them. You want to place the fence in a way that leaves the widest possible gap between the closest individuals on both sides. The wider that gap, the less likely it is that someone will accidentally step over it. That's exactly what an SVM does. It doesn't just separate the data, it finds the best possible separation by maximizing the margin. But here's the twist. Not all data points are equally important. Most of them are far away from the boundary, and they don't really affect where the fence is placed. The only ones that matter? The points that are right up against the margin, the ones that are closest to the boundary. These are called support vectors, and they are the most crucial elements in the entire dataset. Why does this matter? Because instead of relying on all the data points, an SVM only focuses on these few critical points. This makes SVMs incredibly efficient and resistant to overfitting. Think of it like studying for an exam. Instead of reviewing everything, you focus only on the most important, high-impact material. That's why SVMs are so good at handling even small data sets, because they make every data point count. And this idea of maximizing the margin isn't just a theoretical concept, it directly impacts how well an SVM performs in the real world. A wider margin means a more confident, stable decision boundary. A narrow margin, on the other hand, increases the risk of misclassification, especially when dealing with noisy data. But of course, the real world isn't always cooperative. What happens when the data isn't perfectly separable? What if some points end up on the wrong side of the margin? That's where things get interesting. SVMs can soften their boundaries, allowing for a bit of flexibility while still maintaining their structure. And the way they balance this flexibility, that's controlled by something called the regularization parameter, which we'll explore next. Because while maximizing the margin is key, sometimes the best model is one that knows when to bend just a little. Now we're moving from theory to practice. We've seen how SVMs find the best decision boundary, maximize the margin, and rely on support vectors to make decisions. But how do we actually train an SVM model? What does the step-by-step process look like when we go from raw data to a fully functional classifier? It all starts with data pre-processing. Before we even think about training an SVM, we need to prepare the data set. That means cleaning the data, handling missing values, normalizing or standardizing features, and encoding categorical variables if necessary. An SVM, like any machine learning model, is only as good as the data it learns from. Once the data is ready, the next step is splitting the dataset into training and testing sets. Typically, we use an 80-20 or 70-30 split, ensuring that we have enough data to train the model while keeping a portion aside to evaluate its performance. Now comes the real work: choosing the right kernel. This step is crucial because the choice of kernel determines how well the SVM will handle different types of data. If the data is linearly separable, a linear kernel is the best choice. It's simple, fast, and effective. But if the data is more complex, we need to use nonlinear kernels like polynomial or RBF, which transform the feature space into a higher dimension. With the kernel selected, we move on to training the model. The SVM algorithm works by identifying the optimal hyperplane that best separates the classes while maximizing the margin. This process involves solving a constrained optimization problem, ensuring that the support vectors are correctly positioned and that the model is not too strict or too lenient in its classification. But training an SVM isn't just about finding a hyperplane, it's about tuning hyperparameters. The two most important parameters are C, the regularization parameter, and gamma, if using an RBF kernel. The C parameter controls how much we allow misclassified points. A high C means a strict model with fewer misclassifications, but a risk of overfitting. A low C allows for more misclassifications, making the model more flexible but potentially less precise. Gamma, on the other hand, controls how far the influence of a single training example reaches in nonlinear transformations. A high gamma means the decision boundary is heavily influenced by close points, while a low gamma results in a more generalized model. Once the model is trained, we need to evaluate its performance. This is where metrics like accuracy, precision, recall, and F1 score come in. A high accuracy might seem good, but if the data set is imbalanced, other metrics like recall, how well we capture true positives, and precision, how many of our positive predictions were actually correct, become more important. A confusion matrix helps visualize how well the model classifies different categories. And finally, once we're satisfied with the model's performance, we can use it for making predictions. The trained SVM model can now classify new unseen data by determining on which side of the hyperplane each point falls. But here's the big question. What if we're not working with classification at all? What if we need to predict continuous values instead of discrete categories? That's where we shift gears from classification to regression, and believe it or not, SVMs can handle that too. So far, we've seen how support vector machines excel at classification, separating data into distinct categories with the widest possible margin. But what if we're dealing with something different? What if we don't just want to classify data, but actually predict continuous values? That's where support vector regression, SVR, comes in. At first glance, regression might seem like an odd fit for SVMs. After all, we've been talking about decision boundaries, margins, and classification. But instead of drawing a line that separates two classes, SVR does something a little different. It finds a best fit function that predicts a numerical outcome while still maximizing the margin. Let's break it down. Imagine you have a scatter plot of data points, and your goal is to draw a line that best represents the trend in the data. Traditional regression methods, like linear regression, minimize the sum of squared errors, trying to get as close to every data point as possible. But SVM regression, it plays by a different set of rules. Instead of trying to fit all the points exactly, it introduces something called the epsilon margin, a tube around the function where small errors are completely ignored. Why is this important? Because in the real world, not all errors matter. Think about predicting house prices. If your model predicts $250,000, but the actual price is $251,000, does that really matter? Not much. SVR takes this into account by only penalizing large deviations, while completely ignoring minor errors inside the margin. This makes SVR more robust to noise and helps it focus on finding the best overall trend rather than obsessing over every single point. The way SVR finds this function is similar to how an SVM finds a classification hyperplane. It still relies on support vectors, but instead of maximizing the margin between classes, it minimizes the error while maintaining the largest possible margin of tolerance. The width of this margin is controlled by the epsilon parameter. A small epsilon means the model tries to fit the data more closely, while a larger epsilon allows for more flexibility. Just like in classification, we also have the C parameter, which controls the trade-off between allowing errors and keeping the margin wide. A higher C means the model tries to fit more points exactly, risking overfitting, while a lower C means the model is more relaxed and allows for more flexibility. And here's where kernels come back into play. Just like in classification, if the relationship between inputs and outputs isn't linear, we can use kernel functions like polynomial or RBF to transform the input space and capture more complex patterns. SVR is widely used in applications like stock price prediction, weather forecasting, and even medical diagnosis, where small variations in data don't always need to be strictly penalized. It's a powerful approach that balances precision and flexibility, making it an excellent choice for many regression problems. But here's the big question. Now that we've covered both classification and regression, where exactly do SVMs shine the most? What makes them stand out from other machine learning models? That's what we're about to explore next. Now that we've seen SVMs in action, both for classification and regression, it's time to ask the big question. Why use SVMs in the first place? What makes them so special compared to other machine learning models? Let's start with one of their biggest strengths. They work exceptionally well, even with small data sets. Unlike deep learning models that need thousands or even millions of examples to perform well, SVMs can learn effectively from a much smaller set of data. This is because they focus only on the most important points, the support vectors, instead of trying to memorize everything. Then there's the fact that SVMs are built for high-dimensional spaces. Some machine learning models start to break down when there are too many features, but SVMs thrive in these situations. This is especially useful in fields like text classification, bioinformatics, and facial recognition, where the number of features, words in a document, genes in a sequence, pixels in an image is often far greater than the number of training examples. Another major advantage, they are memory efficient. Unlike some models that require storing vast amounts of data, an SVM only needs to remember the support vectors. This makes them particularly useful for applications where computational resources are limited. And then there's the margin maximization principle, the fact that SVMs don't just separate classes, but do so in the best possible way, maximizing the margin between different categories. This leads to better generalization, meaning that SVMs are less likely to overfit the training data and can make more accurate predictions on unseen data. But what about real-world applications? SVMs have been successfully used in handwriting recognition, spam filtering, medical diagnosis, and financial forecasting. Their ability to handle high-dimensional spaces and work well with limited data makes them a popular choice in fields where accuracy is critical. However, SVMs aren't perfect, and there are some challenges that come with using them. One of the biggest is computational complexity. While they work well for small to medium-sized data sets, training an SVM on huge data sets can be slow. The more data you have, the harder it becomes to find the optimal hyperplane, especially when using nonlinear kernels. Another challenge, choosing the right kernel. As we've seen, the kernel trick is one of the most powerful features of SVMs, but selecting the right one can be tricky. The wrong choice can lead to poor performance, and tuning hyperparameters like C and gamma requires careful experimentation. So while SVMs are an incredibly powerful tool, they aren't always the best choice, especially when dealing with extremely large data sets. That's why it's important to understand not just their strengths, but also their limitations, which is exactly where we're headed next. Now that we've talked about all the things that make support vector machines powerful, it's time to flip the coin and look at the challenges that come with using them. Because let's be real, no machine learning algorithm is perfect. One of the biggest drawbacks of SVMs is their computational complexity. While they work brilliantly on small to medium-sized datasets, things start to slow down dramatically when the dataset gets too large. Why? Because training an SVM requires solving a complex optimization problem. As the number of data points grows, the time and memory required to find the optimal hyperplane increase exponentially. This makes SVMs less practical for massive datasets where other models, like neural networks or decision trees, can train much faster. Then there's the sensitivity to parameter settings. Remember the C and gamma parameters? They play a crucial role in how an SVM performs, but tuning them isn't always straightforward. Set C too high and the model becomes too strict, capturing every little detail and overfitting to the training data. Set it too low and the model becomes too relaxed, making overly simplistic decisions. Similarly, gamma controls how much influence individual training points have. Too high and the model becomes overly sensitive to noise. Too low and it struggles to capture patterns in the data. And speaking of challenges, perhaps the most difficult part of working with SVMs is choosing the right kernel. The kernel trick is one of the most powerful aspects of SVMs, but it's also one of the easiest places to go wrong. A linear kernel is fast and simple, but only works well for linearly separable data. A polynomial kernel can capture more complex patterns, but if the degree is too high, it becomes computationally expensive. The RBF kernel is a great general-purpose choice, but setting the gamma value incorrectly can lead to underfitting or overfitting. There's no one-size-fits-all answer, and the best kernel often depends on trial and error. SVMs also struggle when dealing with imbalanced data sets, situations where one class is much larger than the other. Since SVMs focus on maximizing the margin, they might ignore minority class examples if they don't contribute much to the decision boundary. This can be a major problem in applications like fraud detection or medical diagnosis, where the minority class is often the most important. And finally, while SVMs are great at classification, they don't provide probabilistic outputs like logistic regression or neural networks do. In many real-world applications like medical diagnosis or spam detection, it's not just about getting a prediction, it's about knowing how confident the model is in that prediction. SVMs don't inherently provide this kind of probability estimate, making them harder to interpret in some cases. So, while SVMs are undeniably powerful, they aren't always the best tool for the job. When working with massive datasets, deep learning might be a better choice. When interpretability is key, decision trees or logistic regression might be preferred. And when dealing with imbalanced data, specialized techniques like resampling or class-weighted SVMs are often needed. But this brings up an interesting question. How do SVMs compare to other machine learning models? When should you choose an SVM and when should you look elsewhere? That's exactly what we're going to find out next. Now that we've explored the strengths and weaknesses of SVMs, let's see how they stack up against other popular machine learning algorithms. Because in the real world, choosing the right model is everything, and SVMs, while powerful, aren't always the best choice. First, let's compare SVMs to logistic regression. Both are great for binary classification, but they take very different approaches. Logistic regression is simple, fast, and interpretable. It predicts probabilities, which makes it useful in applications where we need to understand the confidence of a prediction. Think medical diagnoses or fraud detection. But here's the catch. Logistic regression struggles with high-dimensional data and complex decision boundaries. That's where SVMs shine. If the data is messy, high-dimensional, or not linearly separable, an SVM with the right kernel will easily outperform logistic regression. Now, what about decision trees? Unlike SVMs, decision trees are intuitive and easy to interpret. They split data into clear, rule-based segments, making them perfect for applications where explainability matters, like finance or healthcare. But decision trees have a major downside. They tend to overfit, especially on small datasets. SVMs, with their margin maximization approach, are much more robust and generalize better. That said, decision trees scale much better than SVMs. So, When working with very large datasets, models like random forest or XGBoost, which are based on decision trees, tend to be preferred. And then there's the big one, neural networks. Deep learning models have revolutionized machine learning, handling tasks like image recognition, speech processing, and natural language understanding with incredible accuracy. So, how do SVMs compare? Well, if you have a huge dataset, deep learning is usually the better choice. It can learn complex patterns that SVMs might struggle with. But SVMs have an advantage in situations where data is limited. Unlike neural networks, which need tons of data to generalize well, SVMs can perform exceptionally well with small data sets. Another key difference, computational efficiency. Training a deep neural network can take hours or even days on large data sets, requiring massive computing power. An SVM, while still expensive on large datasets, is often more computationally efficient for smaller problems. That's why SVMs are still widely used in fields like bioinformatics, where datasets are often small but high dimensional. So, when should you choose an SVM? If you're dealing with a small to medium-sized dataset, high-dimensional data, or a classification problem where you need maximum margin separation, SVMs are a fantastic choice. But if the dataset is huge, or interpretability is key, other models like decision trees, logistic regression, or deep learning might be a better fit. This is why understanding your dataset is critical. SVMs aren't a magic bullet, but when used in the right context, they can outperform many other models. And speaking of real-world applications, where exactly are SVMs being used today? Let's take a look at how they're powering everything from text categorization to facial recognition. Support vector machines aren't just a theoretical concept, they're everywhere in the real world. From text classification to medical diagnosis, SVMs power some of the most critical machine learning applications. Let's take a look at where they shine the most. One of the most famous applications, handwritten digit recognition. If you've ever used a postal service that automatically sorts mail based on handwritten zip codes, there's a good chance an SVM was behind it. The Eminis dataset, which contains thousands of handwritten digits, has been used as a benchmark for machine learning models, and SVMs have consistently achieved near human accuracy in classifying these digits. The secret? Their ability to handle high-dimensional data. Each handwritten digit is essentially an image made up of hundreds of pixel values, and SVMs can efficiently separate different numbers using kernels. Then there's text categorization. Think spam detection, sentiment analysis, and document classification. When you receive an email, your spam filter analyzes the words, phrases, and structure to determine whether it belongs in your inbox or the spam folder. SVMs are exceptionally good at this task because text data is high dimensional. Each word in an email can be treated as a separate feature. Since SVMs perform well in high-dimensional spaces, they've been widely used in natural language processing (NLP) applications. SVMs also play a major role in bioinformatics, where they help classify genes and predict disease patterns. Genetic data is incredibly complex, with thousands of features representing different genes and their expressions. Traditional models struggle with such high-dimensional data, but SVMs can efficiently find patterns and classify genetic variations linked to diseases like cancer. They've also been used to analyze protein structures, helping researchers understand how proteins fold and interact. And let's not forget image classification. Whether it's facial recognition, medical imaging, or object detection, SVMs have been used to classify images in ways that were once considered impossible. In medical diagnostics, for example, SVMs help detect diseases by analyzing X-rays, MRIs, and CT scans. They can differentiate between healthy and diseased tissues, making them valuable tools in early detection and diagnosis. What makes SVMs such a great fit for these applications? Their ability to generalize well. even with small datasets. Unlike deep learning models, which require massive amounts of labeled data, SVMs can achieve strong performance with a relatively small number of examples. This makes them especially useful in fields where data collection is difficult or expensive, like medicine and scientific research. But here's the big question. What happens when we push SVMs to their limits? What if we scale them up for massive datasets or apply them in even more complex environments? That's where things start to get really interesting. Support vector machines are already powerful, but where they truly stand out is in high-dimensional spaces. Most machine learning models struggle when the number of features grows large, but SVMs, they thrive in it. Think about image classification. A simple 100x 100 pixel image has 10,000 features, one for each pixel. Text data, even worse. A document with a vocabulary of 50,000 words can be represented as a feature vector with 50,000 dimensions. Traditional models like logistic regression or k-nearest neighbors break down in these scenarios because they struggle to find meaningful patterns when there are more features than data points. SVMs, however, are built for exactly this kind of problem. Why? Because they don't rely on all the data points. They focus only on the support vectors. Instead of getting lost in the complexity of the feature space, they zero in on the most important points that define the decision boundary. This makes them highly efficient in complex spaces where most other algorithms would fail. Take genomic research as an example. DNA sequences contain thousands of genetic markers, but only a handful are truly relevant for classifying diseases. SVMs excel in these cases because they automatically filter out irrelevant features and focus on the critical data points that matter. That's why they're widely used in bioinformatics, drug discovery, and medical diagnosis. Another reason SVMs are so effective in high-dimensional spaces is the kernel trick. When working in very high dimensions, it's nearly impossible to visualize patterns, let alone separate classes using a straight hyperplane. But with the right kernel, SVMs can map data into an even higher dimensional space where a clean separation becomes possible. This is exactly why RBF kernels are so popular in image recognition and medical imaging. They allow SVMs to find patterns that would be impossible to detect otherwise. But there's a trade-off. While SVMs are fantastic in high-dimensional spaces, they become computationally expensive as datasets grow larger. The same mathematical optimizations that allow them to work so well also mean that training time increases significantly as the dataset expands. That's why when dealing with truly massive datasets, millions of samples instead of thousands, deep learning models start to take the lead. So, where's the sweet spot? When the dataset is high-dimensional but not too large, SVMs often outperform deep learning models, especially when labeled data is limited. That's why they're still widely used in applications like medical diagnostics, facial recognition, and text classification, where feature spaces are large but data collection is difficult. But efficiency isn't just about handling lots of features. It's also about using only the most important ones. And that brings us to another major strength of SVMs: memory efficiency. One of the most underrated strengths of support vector machines is their memory efficiency. Unlike many machine learning models that need to store and process huge amounts of data, SVMs are incredibly selective. They only focus on the most critical data points, the support vectors. Let's break it down. Imagine you're given a massive dataset with thousands or even millions of samples. Most machine learning models, like neural networks or k-nearest neighbors, need to store and compute with all the data points, which quickly becomes expensive in terms of memory and processing power. But an SVM, it ignores most of the dataset and works only with the handful of points that are closest to the decision boundary. These are the support vectors, and they're the only ones that matter when determining the hyperplane. This selective approach gives SVMs a huge advantage when working with limited computational resources. Since they don't need to store the entire dataset in memory, they can be deployed in environments where memory is a constraint, such as embedded systems, mobile devices, and real-time applications. That's why SVMs have been used in real-time facial recognition, medical imaging, and even edge AI applications. Another major benefit of this efficiency is that SVMs are less prone to overfitting. Many machine learning models, especially deep learning networks, tend to memorize the training data, which can lead to poor generalization on unseen data. SVMs, however, naturally resist overfitting because they focus on the margin, not just the individual training points. By maximizing the margin, they ensure that the decision boundary is as stable and generalizable as possible. But of course, there's a trade-off. While SVMs are memory efficient in terms of storage, training them can still be computationally expensive, especially on very large datasets. The reason? Finding the optimal hyperplane requires solving a quadratic optimization problem, which becomes more difficult as the number of training samples increases. That's why SVMs are often preferred in scenarios where feature spaces are large, but datasets are not excessively huge. This efficiency also makes SVMs a great choice for transfer learning, where you train a model on one dataset and apply it to another with similar characteristics. Since SVMs rely only on a few critical points, they can often adapt well to new environments without needing to retrain on massive amounts of data. But here's the real challenge: choosing the right kernel function. Because while SVMs are efficient, their performance depends heavily on how well the data is transformed, and that's where the real strategy comes into play. One of the most critical decisions when working with support vector machines is choosing the right kernel function. The kernel is what allows SVMs to handle complex, nonlinear data by transforming it into a higher dimensional space where separation becomes possible. But here's the catch: choosing the wrong kernel can make or break your model. So, how do we decide? It all starts with understanding the data. If the data is already linearly separable, a linear kernel is the best choice. It's simple, fast, and works well for problems like text classification, where the number of features is often much larger than the number of samples. But when the data is more complex, we need something more powerful. That's where nonlinear kernels come in. The polynomial kernel captures feature interactions and works well for problems where relationships between variables aren't strictly linear. However, as the degree of the polynomial increases, computation time skyrockets, making it impractical for large datasets. The radial basis function, RBF. Kernel is the most widely used because it can model highly complex relationships. It maps data into an infinite dimensional space, making it ideal for image recognition, bioinformatics, and other intricate datasets. However, tuning the gamma parameter is crucial. Too high, and the model overfits. Too low, and it underfits. The sigmoid kernel, inspired by neural networks, is less commonly used, but can be effective in scenarios where data behaves similarly to a logistic function. But selecting the kernel isn't just about intuition, it's about testing and validation. The best way to determine which kernel works best is through cross-validation, where we test different kernels on subsets of the data to see which one performs best. This ensures that we're not just choosing a kernel that fits the training data well, but one that generalizes effectively to unseen data. There's also a trade-off between complexity and interpretability. Linear kernels are easy to understand and explain, while RBF kernels, though powerful, transform the data into a space that's nearly impossible to interpret directly. That's why in some fields, like medicine and finance, simpler models are sometimes preferred for their transparency. But the choice of kernel isn't the only thing that matters. Hyperparameter tuning plays a massive role in the final performance of an SVM. Parameters like C and gamma control how strict or flexible the decision boundary is, and setting them correctly can make the difference between a perfect classifier and one that completely fails. So, once we've chosen the kernel, how do we fine-tune these parameters for optimal performance? That's where hyperparameter tuning comes in, and it's the next key step in mastering SVMs. Because even the best kernel won't perform well if the model's parameters aren't optimized. Support vector machines have two key hyperparameters that directly impact performance, C and gamma. Tuning them correctly can mean the difference between a model that generalizes well and one that either overfits or underperforms. Let's start with C, the regularization parameter. C controls the trade-off between a wide margin and classification accuracy. A low C means the model is more tolerant of misclassified points, leading to a wider margin but a higher chance of errors. A high C, on the other hand, tries to classify every training point correctly, leading to a narrower margin and a model that might overfit. The challenge is finding the sweet spot, where the margin is large enough for generalization, but not so large that the model loses accuracy. Then there's gamma, which comes into play when using RBF or polynomial kernels. Gamma controls how much influence a single training example has. A low gamma means each point has a large influence, resulting in a smoother decision boundary that may underfit the data. A high gamma means points have a very local influence, leading to highly complex boundaries that might overfit. If gamma is too high, the model memorizes the training data, performing well on it but failing on unseen examples. But how do we find the best combination of C and gamma? That's where hyperparameter optimization techniques come in. Grid search. This is an exhaustive method where we test multiple values for C and gamma in a predefined range, systematically checking which combination performs best. It's thorough, but it can be computationally expensive. Random search. Instead of testing every possible combination, random search picks random values within a range. It's faster than grid search and often finds near optimal values with less computation. Bayesian optimization, a more advanced technique that intelligently selects hyperparameter values based on past performance, gradually improving efficiency and accuracy. To ensure the model is truly optimized, cross-validation is used alongside hyperparameter tuning. Instead of just testing on a single training and validation split, the dataset is divided into multiple folds, and the model is trained and evaluated on different subsets. This prevents overfitting and helps us determine the best parameters that generalize well to new data. Ultimately, tuning an SVM is a balance between flexibility and stability. Too much complexity and the model memorizes the data instead of learning patterns. Too little and it oversimplifies, missing key relationships. Once we've fine-tuned our SVM, it's time for the real test, implementing it in Python and seeing how it performs on actual data. Because understanding SVMs in theory is one thing, but applying them in the real world, that's where things get really exciting. Let's bring all this theory to life. Understanding SVMs in theory is one thing, but actually implementing them, that's where the real magic happens. So let's dive into how we build an SVM model step by step using Python. It all starts with the data. Raw data is messy. It might have missing values, outliers, or features that are on completely different scales. Before training an SVM, we need to clean it up. That means handling missing values, normalizing numerical features so they're on the same scale, and encoding categorical variables into numbers that the model can understand. In Python, we use pandas for data wrangling and scikit-learn for pre-processing. This ensures that our model learns from clean, structured data instead of getting confused by inconsistencies. Next, we need to split our dataset. We can't just train on all the data and hope for the best. We need to leave out a portion of it, usually 20%, for testing. This allows us to evaluate the model on unseen data and see how well it generalizes. A model that performs well on the training data but fails on new data, that's overfitting, and we want to avoid that at all costs. Now it's time to build the actual SVM model. In Python, it takes just a few lines of code. We use scikit-learn's SVC class to create the model. This is where we decide which kernel to use, linear, polynomial, or RBF. If the data is simple and linearly separable, a linear kernel works fine. But if the patterns are more complex, RBF is usually the best choice. We also set our hyperparameters like C and gamma, which we tuned earlier to get the best performance. Then comes the training step. This is where the SVM learns from the data, figuring out the optimal hyperplane that separates the classes with the widest possible margin. Training is quick on small datasets, but can take longer on larger ones, especially with complex kernels. Once training is done, the model is ready to make predictions. Now we test it, we feed it the test data and compare its predictions to the actual labels. But raw accuracy isn't enough. We need a deeper evaluation using precision, recall, and F1 score. These metrics tell us more about how well the model is handling different types of errors. For example, if we're classifying emails as spam or not spam, we don't just want high accuracy. We want to minimize false positives, where important emails get mistakenly classified as spam. If we're dealing with two-dimensional data, we can even visualize the decision boundary. With a little bit of plotting, we can see exactly how the SVM is dividing the space between classes. It's a great way to get an intuitive sense of how the model is working. And just like that, we've built a working SVM classifier. A few lines of code, some careful tuning, and we have a powerful model ready to classify new data. But classification is only one side of the coin. What if instead of predicting categories, we need to predict continuous values, like house prices, stock trends, or temperature forecasts? That's where support vector regression, or SVR, comes in. And the way it works might just surprise you. Once we've trained an SVM model, how do we know if it's actually good? Accuracy alone isn't enough. We need to go deeper because in the real world, misclassifications have consequences. Imagine a medical diagnosis model. Would you rather focus on overall accuracy or make sure the model never misses a serious disease? That's why we use performance metrics to truly understand how well our model is working. One of the most important tools is the confusion matrix. It gives us a complete picture of how our model is classifying data by breaking down predictions into 4 categories: true positives, true negatives, false positives, and false negatives. A model might have high accuracy, but if it's misclassifying an important class more often, that's a problem. For example, in fraud detection, a false negative, where a fraudulent transaction is classified as legitimate, could be catastrophic. Then we have precision, recall, and F1 score. 3 metrics that help us go beyond accuracy. Precision measures how many of our positive predictions were actually correct. It's crucial in cases where false positives are costly, like in spam detection, where we don't want important emails mistakenly sent to the spam folder. Recall, on the other hand, tells us how well we are identifying all the true positives. It's critical in medical diagnoses. If a model predicts cancer, we want it to catch every single case, even if that means a few false positives. Since precision and recall often work against each other, we use the F1 score as a balance. It's the harmonic mean of precision and recall, giving us a single number that represents the model's effectiveness. A perfect F1 score of 1 means our model has both high precision and high recall, something that's rarely achieved in real-world data. But we don't just stop there. Another key metric is the ROC curve, Receiver Operating Characteristic Curve, which helps us visualize how well our model distinguishes between classes. It plots the true positive rate against the false positive rate at different classification thresholds. A model with a perfect ROC curve sits at the top left corner, meaning it's making almost no mistakes in classification. And if we're dealing with an imbalanced data set where one class is much larger than the other, accuracy becomes even more misleading. Imagine a fraud detection model where only 1% of transactions are fraudulent. If the model predicts not fraud 100% of the time, it still has 99% accuracy, but it's completely useless. That's why metrics like precision, recall, and AUC are more reliable in these cases. Evaluating an SVM isn't just about checking a few numbers, it's about understanding what the model is good at and where it struggles. If precision is low, we might need to fine-tune C or gamma. If recall is suffering, maybe we need a better kernel. Every metric tells us something different, and by analyzing them together, we can fine-tune the model to make it truly effective in the real world. But what happens when we move from theoretical datasets to real-world case studies? What does an SVM look like when it's applied at scale, solving real problems? That's exactly what we're going to explore next. Now let's take everything we've learned and see how SVMs work in a real-world case study. Theory is great, but nothing beats seeing an SVM in action, solving an actual problem. One of the most well-known applications of SVMs is in handwritten digit recognition, using the MNIST dataset, a dataset of thousands of images of handwritten numbers from 0 to 9. Think about how we as humans recognize digits. We don't measure every pixel, we look at shapes, curves, and patterns. SVMs do something similar, except they rely on high-dimensional feature spaces to distinguish between digits. Each image in the MNIST dataset is a 28x 28 pixel grid, meaning each image has 784 features, one for each pixel's intensity. That's an incredibly high-dimensional space, but SVMs are designed to handle exactly this kind of problem. The process starts with data preparation. Each image is flattened into a vector of pixel values and normalized so that all features are on the same scale. This helps the SVM learn efficiently without being affected by differences in lighting or contrast. Next comes choosing the right kernel. Since digit recognition is a nonlinear problem, a linear kernel won't work well. Instead, we use an RBF kernel, which allows the SVM to map the pixel data into a higher dimensional space where separation becomes easier. Once the model is trained, we test it on new, unseen handwritten digits. And the results. SVMs achieve over 98% accuracy on MNIST, making them one of the best performing models for handwritten digit recognition, especially when data is limited. What's really impressive is how efficient SVMs are compared to deep learning. While neural networks like CNNs, convolutional neural networks, now dominate image recognition, they require massive amounts of data and computational power to train. SVMs, on the other hand, can achieve high accuracy with far fewer training examples, making them a great choice for scenarios where collecting labeled data is difficult. But digit recognition is just the beginning. SVMs have been used in medical diagnosis, detecting diseases based on high-dimensional genetic data. They're widely applied in financial fraud detection, classifying transactions as fraudulent or legitimate. They've even been used in facial recognition, analyzing key features to distinguish one person from another. This case study highlights why SVMs are still widely used today. They're incredibly effective in high-dimensional spaces, they work well even with small data sets, and they generalize well to unseen data. But as powerful as SVMs are, the world of machine learning is constantly evolving. What does the future of SVMs look like? Will they continue to be relevant, or will deep learning take over completely? That's what we're about to find out. The world of machine learning is constantly evolving, and support vector machines, despite being a well-established method, continue to play a significant role in the future of AI. While deep learning has gained dominance in areas like image recognition and natural language processing, SVMs still hold their ground in scenarios where data is limited, interpretability is crucial, and computational efficiency matters. One of the key advancements in SVMs is optimization techniques that make them faster and more scalable. Traditional SVM training can be computationally expensive, especially with large data sets, but new approaches, such as parallel processing, GPU acceleration, and approximation methods, are making SVMs more efficient. Techniques like linear time, SVM solvers, and stochastic gradient descent-based optimization are reducing the time and memory required to train large-scale SVM models. Another major trend is the hybrid approach, where SVMs are combined with deep learning. For example, in computer vision tasks, deep learning models can be used for feature extraction, while an SVM acts as the final classifier. This hybrid approach has been used in medical imaging, where deep learning extracts patterns from MRI scans, and an SVM classifies them as cancerous or non-cancerous with high accuracy. In natural language processing, SVMs are still widely used for text classification, spam detection, and sentiment analysis, especially when computational resources are limited. While deep learning models like transformers have taken over large-scale NLP tasks, SVMs remain a reliable choice when working with small to medium-sized datasets. Another area where SVMs are expected to grow is in quantum computing. Researchers are exploring quantum SVMs, which leverage quantum mechanics to solve classification problems exponentially faster than classical SVMs. This could revolutionize fields like cryptography, drug discovery, and high-dimensional data analysis. Additionally, automated hyperparameter tuning using AI-driven techniques is improving SVM performance. Instead of relying on grid search or random search, advanced methods like Bayesian optimization and genetic algorithms are being used to automatically find the best C, gamma, and kernel parameters, making SVMs easier to deploy without extensive manual tuning. While deep learning continues to dominate in large-scale unstructured data problems, SVMs remain highly relevant in structured, high-dimensional, and small data environments. Their robustness, ability to handle high-dimensional feature spaces, and strong theoretical foundation ensure that they will continue to be an important tool in the machine learning landscape. So, what's the final takeaway? What have we learned about SVMs, and where do they fit into the bigger picture of machine learning? Let's summarize everything we've covered. Support vector machines have taken us on an incredible journey, from understanding the basic idea of hyperplanes and margins to exploring advanced concepts like kernel tricks, hyperparameter tuning, and real-world applications. Now, let's bring everything together and answer the big question. Where do SVMs fit into the bigger machine learning picture? At their core, SVMs are powerful, adaptable, and reliable. They excel in high-dimensional spaces, work well even with limited data, and focus on the most important support vectors, making them both efficient and robust. They might not be the fastest for massive data sets, but when the problem demands precision and clear decision boundaries, SVMs often outperform more complex models. We've seen how they are used in handwritten digit recognition, spam filtering, bioinformatics, fraud detection, and medical imaging. Their ability to find patterns in structured, high-dimensional data has kept them relevant, even in an era dominated by deep learning. And with improvements in optimization, hybrid models, and even quantum SVMs, they continue to evolve. But SVMs aren't a one-size-fits-all solution. When working with huge datasets, deep learning models might be a better choice. When interpretability is a priority, decision trees or logistic regression might be preferred. And when handling imbalanced data, additional techniques like resampling or class-weighted SVMs may be needed. The key takeaway? SVMs are not outdated, they are specialized. When used in the right context, they can outperform more complex models with fewer data points and computational resources. Their mathematical foundations make them a powerful tool in any machine learning arsenal. So whether you're building a classification model, experimenting with feature-rich data, or tackling a high-dimensional problem, knowing how and when to use SVMs gives you an edge. Machine learning is all about choosing the right tool for the right job, and SVMs remain one of the most reliable, precise, and efficient tools out there. With that, we've completed our deep dive into support vector machines. The next step, try them out for yourself. Implement an SVM in Python, experiment with different kernels, tune the hyperparameters, and see how they perform on real-world datasets. Because at the end of the day, the best way to master machine learning is to start building.